These two R's are confusing, road and rain. So road is like ground. That R is for rain. We have to find speed and direction of rain with respect to the road, VRG. That equation will be true for both conditions. There are two conditions, right? You can apply the same equation here also, the same equation here also. Here it's a 90-degree type of situation. So one vector here, one vector here. Resultant of the two VRG will be somewhat like this. Let's use one technique in solving this question. That technique is that when two vectors are equal, then their various components are also equal. Yes, go ahead.
Sir, is the speed of rain 24 kmph?
No. It's not. So when two vectors are equal, their components are also equal. Concentrate on the left side case. VMG, VRM. Their sum would be somewhat like this. And that is this vector, VRG. Let's say rain makes angle of theta with vertical. Our equation is this. We are dealing with two vectors, so their components will be equal. Considering horizontal component, it will be VRG. This angle is theta, that should be VRG sine theta, right? And that one should be VRG cos theta. Now, right side you have sum of 2, and this vector, this component is this. This whole thing is one vector whose this component is this, VMG. And that is sine theta component of VRG. VRG sine theta will be VMG, and VRG cos theta will be VRM. Any questions up to this point, let me know. Very well. Now what is VMG 8? VRM we don't know. No problem. At least one equation we can use. VRG sine theta equal to 8. Right? This equation has got VRM, and VRM is something that we do not know. So let's not bother about this. One equation we have got, and we are solving for two variables, right? For magnitude and for angle. Two variables. So mathematically we need two equations. One equation we got from case number 1. Second equation we hope to get from case number 2. So looking okay. Case number 2. Yes, go ahead.
No sir, I got it.
Okay. Case number 2. That I can write in this board itself, this screen itself. For this case, also we can apply the same concept. If two vectors are equal, their components are equal. I'm just redrawing this. VMG 12, VRM, that's making 30 degrees from vertical. VMG, VRM. And their vector sum, RM, MG, that should be VRG. That one. VRG. Theta is the angle that we took, that rain is making with vertical, right? That angle won't change. If you run more quickly or you run less quickly, what does it have to do with rain falling at certain angle from vertical? That has nothing to do with the angle at which rain falls with respect to the ground. That has nothing to do with the speed at which rain falls with respect to the ground. These things may change with respect to you, not with respect to ground. So VRG and this theta, that is not going to change in the two cases. So it's the same theta here, right? All right, now we are going to equate the components. Horizontal component of VRG will be how much? This will be cos theta, this will be sin theta. So VRG sin theta. And then these fellows, the component on the right side, VMG fully is coming on the right side. And this fellow is coming partly. VRM. This angle is 60. This is 60. So VRM cos 60 left side. That I must subtract. Minus VRM cos 60. Right? So this vector is equal to this. So component of it on this side will be equal to component of this side also, the same direction. VMG will come fully. VRM will not come fully. VRM cos 60 and that too in this side, so minus sign will come. Any questions? Now, the vertical components, yes, go ahead. Go ahead.
Sir, what is this thing, or why we have used this thing?
Why we have used that thing? Because we are equating the components of the vectors, left side and right side. How do you find the component of this vector on this direction? VMG is fully on this direction, so that you are copying. How about VRM? Won't you find its component in this direction? So we are finding VRM's component in this direction. That's why this is 60, so VRM cos 60 is this. Vertical. VRG cos theta here down. And then right side, VMG will not have anything on the down direction. VRM will have. What is VRM's component in this direction?
So it would be VRM cos 30 degrees or VRM sin 60 degrees.
VRM cos 30. VRM cos 30. So I will try to explain this procedure little bit more. The procedure is that if two vectors are equal, then their components are equal. This is a very good strategy in getting multiple equations. Why is it a great strategy? In mathematics, the general rule is that if you want to solve for two variables, you need two equations. That's a general rule in mathematics. And in vectors, one equation can often give you 2 to 3 equations. One vector equation can give you 2 to 3 equations. Look at that. Vector A equal to vector B is just one equation, but it's a vector equation. It's giving you 3 equations: AX equal to BX, AY equal to BY, AZ equal to BZ. One vector equation is capable of giving you 3 equations. Sometimes it could be a one plane thing, 2 components for one plane thing, like the problem that we are doing. It's not a 3D problem, but it's a 2D or a plane problem. In plane problem, you may have to deal with only X and Y, basically 2 things, 2 dimensions. So 2 equations it can give you. In complex numbers also you will find that one equation will be able to give you 2 equations. One equation in complex numbers will be able to give you 2 equations. That's the advantage of this technique. If you have got little more complication, like you have A equal to B plus C, this is exactly what we had. Rule is still the same. X component on the left side is equal to X component on the right side. Y component on the left side, Y component. Z, Z. So that's what we are trying to do here. This is like A equal to B plus C type of situation. So we are finding 2 equations. We are finding 2 equations. One for this direction and one for that direction. For this direction, we got this one. This is for this direction. And this is for downward direction. This was a little easy because VMG was already in that direction. If a vector is already in this direction, how can it have a perpendicular component? So our job became little easier for this part. But if VMG were not horizontal but somewhat inclined, then in that case VMG would contribute to some component in downward direction. So this became little easy. Any questions? Let me know. Now, one problem is that of VRM. VRM we don't want, but I can get rid of that. Yes, that can be handled. So let's find VRM from here and plug it in here. VRG cos theta cos 30. Coming to this side, cos 30 will become that, and that is VRM. That I'm going to put here. And then it would be VRG sin theta. VMG is how much? VMG is how much? That you should be able to tell.
Sir, 8 kilometers per hour.
Which case are we discussing? Left or right?
Sorry, sir, 12 kilometers per hour.
12. cos 60. So that's second equation. Two variables, two equations. Let me copy this. Take it to the next board. In this board, one equation is already written. This one. VRG sin theta is 8. That means 8 plus this 12. That means VRG cos theta is 4 root 3. Now it should be very easy. Square and add. $64, 48. $112. Well, just see how much you can simplify that 112 thing. Is divisible by 16. Four root 7 kmph. We have to find the direction also. That should be very easy. Dividing these two. Tan theta is equal to 8 by 4 root 3. That is 2 by root 3. Theta equal to tan inverse 2 by root 3. That's it. Now I would let you change the board. Just go through other screen as well. And in case you have any question, then let me know. Yes.
Sir, in that VRG cos theta is equal to 4 root 3. Below there is something 2, sir. I'm not clear what is that.
That is square. We have considered these two equations. Star and hash. We have squared them and added them, the two equations.
Fine, sir.
So that thing is 2. Any other question? So then I suppose we can move on. Now this is very important. When river is flowing, then you are sort of pushed by it. Two things can be of great interest. Shortest time. You just want to reach the opposite shore as quickly as possible. In that case, the rule is that just do not waste fraction of your velocity. Just do not waste fraction of your velocity. What do we mean by fraction of velocity? Perpendicular things don't support or oppose each other. Perpendicular things. They are sort of indifferent from each other. What is happening is that when you go at some angle, your velocity has two components. One along the river or opposite, other one perpendicular to it. That's a general situation at some angle. Along or opposite or perpendicular. If you just keep perpendicular component, no other component at all, your velocity is pure vertical, then you're not really wasting any velocity to fight with the river. You are telling river that I don't care where you take me, but I'm not going to waste my energy. I'm just going to go vertical. That's it. That's the best policy if you want to reach as quickly as possible. Just go perpendicular. With respect to the river. With respect to the river, go vertical. So you just tell the river that I'm not going to oppose you at all. I don't care actually how you are taking me. You take me wherever you want. I will go absolutely perpendicular with respect to you. Perpendicular vectors are sort of independent situations. So in that case, river will push you to the right, but that is not at the cost of your effort. You're not making any effort in that direction of the river. You're just going perpendicular with respect to the river. So with respect to the river, you go perpendicular. River will push you to the right. You will not reach this point. You will reach somewhere here. That's okay. Your intention was to reach the opposite shore as quickly as possible, not where in that opposite shore. So that's the strategy for shortest time. Go perpendicular with respect to the river. And let river push you if it wants to, no problem. Okay? That is for shortest time. But yes, distance is becoming long. That's your distance as seen by an observer from somewhere here. You will actually be traveling like that as he sees. But you take shortest time. Second case. Now this time you are simply lazy. You just want shortest distance. Shortest distance is a perpendicular distance. So you just want to go like that. As seen by this fellow, you should be going absolutely straight. That is the shortest distance. So because river pushes you to the right side, this time you are going to oppose the river. You are telling the river, no, I'm not going to surrender to you. I'm not going to get pushed to the right side even by an inch. So if you push me to the right by 1 inch, I will go to the left by 1 inch. I'm going to simply cancel your effect. You are cancelling the effect of the river's velocity here. You are acting against the river here partly. So you are going in this direction such that the river pushes you and you reach here. So with respect to the river, you are going like that, this way. The river pushes you to the right side. So somebody from the ground sees that you have gone absolutely straight. And you will reach the exactly opposite point on the other side. And you have traveled the shortest distance by this approach. But you have opposed the river in this case. It's like saying that a component of your effort has struggled. A component of your effort has struggled with the river, sort of that. And in this case, no component of your effort is struggling with the river. It's indifferent attitude, or I don't care type of attitude, where the river takes me. I'm going to go absolutely perpendicular to the river. So for both cases, these should be the approaches. Now I will take some application which will clear this. I think in some questions we have possibly already done these cases. Let me check. You can also check your notes. See the problems that we have done. Have we done these two types of cases? The person just goes perpendicular to the river stream with respect to the river stream in one case, and in the other case the person just wants to reach the opposite point. One question we have done in which the swimmer with respect to the water goes perpendicular to the current. That we have done. Its answer was 5 km/h speed and 53° angle or 37° angle. You found it? A swimmer can swim in still water at 4 km pH. If he swims in a river flowing at 3 km pH and keeps his direction with respect to water perpendicular to the current, find his velocity with respect to the ground. That was the question. So that one. Here what will happen? He is going perpendicular to the current. So which case is it? This or this?
So shortest distance.
Anybody else? He is going perpendicular with respect to the river. No. With respect to the river, he is going perpendicular. Won't the river push him to the right and will he not reach here? How can it be shortest distance? He keeps his direction with respect to the river perpendicular. As seen by the ground, it is not perpendicular. As seen by the river, it is perpendicular. As seen by the ground, it is this. So which case is it? Shortest time, shortest distance?
So shortest time.
Shortest time. So that question did not ask for the time, but it was for that case only, shortest time. And then if I remember correctly, we did this question also. Just see your notes. A man can swim in still water at a speed of 3 km pH. He wants to cross a river that flows at 2 km pH and reach the point directly opposite to his starting point. In which direction should he try to swim? How much time will he take to cross the river if the river is 500 meter wide? You remember that 500 meter wide river problem? Now in this problem, he wants to reach point that is directly opposite. So which case was it actually? He actually wants to reach here. Which case was it? This or that?
So shortest distance.
Shortest distance. So we have done actually both cases already. So, shortest possible time, that case. So tell me, how should he move? How should he move for shortest possible time?
Sir, he should move perpendicular to the river with respect to the river.
Perfect. So with respect to the ground, if the river is flowing to the right side, Will he finally reach the right side, left side, or exactly opposite point?
Sir, he'll get somewhere the right side of the other river.
Correct. So here we go. With respect to water is 3. Fine. And he wants to go straight with respect to the river. So velocity of swimmer with respect to river. But then river will push him. That is velocity of river with respect to ground. And then this triangle law of vector addition should give us velocity of swimmer with respect to the ground. That should be very easy because it's 90-degree case, right? 90-degree case is easy. So we have VSG equal to VSR plus VRG. Now, can you try to do it after this point? It's a 90-degree case. Well, you should have got the answer already. You see, different people may see different things, but time is same for everybody.
Sir, 4 kmph. 4.
Time you have to tell. Are you telling 4 hours?
Wait 10 minutes.
Yeah, yes, I heard it. You said 10 minutes. Anybody else? I think if you use this particular fellow, then it should be the easiest because this fellow will travel exactly 500 meters. It's not really wise to choose VSG because this distance you don't know. But this distance you do know. So choose this and apply speed equal to distance upon time. And VSR is something that you already know. 3. So speed equal to distance upon time.
It comes to 10 minutes.
10 minutes. So time is 1 by 6 hours. So it is 10 minutes. Any questions? Let me know. This information looks redundant information. We did not need this information for this question, 5 kmph. Isn't it interesting? Even if it is 10 kmph, answer won't change. If you think psychologically, then it may look somewhat frightening that river is traveling so fast. Okay, if not 10, then 100 will certainly look frightening. But theoretically speaking, even if river is traveling at 100 kmph, which could be terrible, the answer won't change. Answer won't change. It will be 10 minutes only. But then if river is traveling at 100 kmph, where will you reach? Like that. So far on the right side. It will be difficult to swim also under that conditions. All right, any questions? Let me know. How to do this type of problem? Once we discuss that, you can handle other variations. In place of triangle, it could be pentagon or it could be hexagon, whatever. The general approach to solving such problems. Let's see. A is always going towards B. B is always going towards C. And C is always going towards A. Now this can be actually quite complicated because the moment stopwatch is pressed, A will go in this direction, but B would have gone here, reached here. Seeing that B is there, A will change its direction towards B, slight change. I may have to exaggerate that a bit, otherwise you won't see the difference. And then B also sees that C has reached here, so B also changes its direction. And likewise, C also does the same thing. And then when A reaches here, B would have reached even further. So continuous change will take place in everybody's motion. But following the argument of symmetry, there is no reason why they should meet at any other point except the centroid of the triangle. I hope you are able to visualize this. as seen by B, who is somewhere else, A will follow a curved path, B will follow a curved path, C will follow a curved path. If you want to find time, will you do it by distance upon speed formula for D, this distance divided by speed? How will you find this distance? It's a curve of unknown type. Which curve is it? We don't know. It's going to be very difficult if you try to do it with respect to D. D is okay for visualization. We will use that concept that different people may see different types of journeys, but time is same for everybody. Time is same for everybody. Why not see everything with respect to B? Why not see everything with respect to B? If B is our observer, then B is not moving, isn't it? If you are inside a train and you are not seeing outside, do you really feel you are moving? You are moving on Earth with such a great speed. Earth is spinning and revolving around the Earth. Do you feel you are moving? No. So when you are in motion, you don't have to feel it. So when B is moving, B doesn't feel it. B is stationary. If B is our observer, B is stationary. And what does B see? Let's say B is watching A. B is just watching A. That's it. B is just watching A. A is always coming towards B. So B sees that A is chasing me. A is just coming straight towards me. Straight is the word B will use, not the curve. Straight. A is coming straight towards me. That's what B will say. But then, how much straight? I mean, how much distance has A traveled with respect to B? Can anybody answer that? Yes, go ahead.
Sir, as you said that B is watching A, and it thinks as A is coming straight towards me. So we take each and every case in that way. Like we would see B straight coming.
Don't worry. Don't worry about others. You just want to know the time, right? You just want to know the time. So just let B watch A alone. Don't bother about anybody else.
Okay.
So my question is, when B is watching A is coming towards it, how much distance does A travel when it reaches B?
Approximately A to that meeting point.
B is the observer. So B is not moving. B is here. So what will B say? How much has A traveled to reach B?
AB, distance AB.
That's it. AB distance, which is D. Which is D. If B is the observer, B is not moving at all. B is right there. So if A wants to reach B, A has to travel that much distance. And A is traveling straight. This is what B will say. D will say different thing. So B says that A travels distance D and meets me. time is distance upon speed, relative speed. We are doing it with respect to B. Now, what is the magnitude of relative velocity? Velocity of A with respect to B. What is the magnitude of that? What we want is D upon B, AB magnitude. Velocity of A with respect to B. That should be easy, isn't it?
V.
Just a moment. A is traveling like this. B is traveling like this. The two vectors are making 120-degree angle. This one is VA. This one is VB. And the question is, what is velocity of A with respect to B, its magnitude? Yes, what's your answer?
So simply V.
Can you repeat?
E.
You need to recheck. VAB is given by VA respect to O, if you like, minus VBO. So it's like saying the VA plus VOB. VAO, VOB. If this is VB, this will be VOB. This is 60 degree. This vector plus this vector. If you like, think like this. Minus VB. This is VB, this is minus VB. Just a moment. That should be plus. VAO plus this. So this vector plus this vector. Formula, square of the first, square of the second, 2 times VA, VB, cos of this angle, 60. And then under root of the whole thing. But VA is equal to VB. Cos 60 is half. Oh, in fact, it's going to be simpler than this. I can delete all this. Relative speed, in that direction it should be. So I should write component of relative velocity of A with respect to B along AB. Magnitude of that. Component only I want along AB, and that can be very easily found. Velocity of A is already along AB. Then VB is not along AB. So VB cos 60. VB cos 60. Yes, that is along BA. That will be subtracted. In fact, added, eventually speaking, because when two velocities are in opposite directions, they add. Relative velocity when we find, then they add. So if we look at VB cos 60, then VB cos 60 is going towards A. VA is going towards B. Yes. But magnitude of VA is V. This is V. Cos 60 is half. So 3V by 2. 3V by 2. That means 2 by 3 D by V. Now let me know if you have any questions.
So why you do VB cos 60?
Yes, it's like this. When one train is going in this direction, other train is going in this direction. This is at 60, this is at 30, kmph, kmph. Then this train will say that velocity of this train is 60 plus 30. Now consider one train going in this direction, other train going in this direction. This is 60 and this is 30. But the angle between them, let's say this is theta. And you are interested in knowing how quickly this distance will be covered. This distance. How quickly this distance will be covered. Now this train is approaching this train with what speed to cover this distance? Now it will be not full 30 which is coming towards it. It is a component of 30. 30 is not degree, it's kmph. Theta is degree. Full 30 is not coming towards this train. A component of 30 only is coming towards this. So to cover this distance, who will help? 60 plus 30 cos theta. This will help to cover this distance. In this case, who will help to cover this distance? This, 90. So here we had a similar situation. Which component of B will be helping in covering this distance? VB cos 60. VB cos 60 is going towards A basically. VA is going towards B and VB cos 60 is going towards A. So they will add. Yes, anything else? Okay. Now in place of triangle, consider a hexagon. In place of triangle, consider a regular hexagon. Right? Regular hexagon whose side is D. There are 6 particles. Each particle has got speed v. The rule is the same. Everybody tries to go towards its neighbor. Just like here, B was going towards C. There also similar thing is happening, but it is happening with all the 6 particles. So obviously they will meet at the center of the hexagon eventually. The question is, how much time will it take for them to meet? That's the question. Right? So it is for hexagon. That's your assignment for hexagon, regular hexagon. We stop now.